and the title of the talk is Improvements to ME 3160, and that means nothing to anyone here, but ME 3160 is a junior senior level mechanical engineering laboratory class. We call it thermal fluids engineering, and it is, or has traditionally been, a sequence of laboratories that are meant to clarify issues for mechanical engineers, issues in thermodynamics and fluid mechanics mainly. It has had a pretty much set and prescribed set of laboratories that students move through, and that's been true for probably 20 years. And in our ABET review, we were spanked to some degree because they said, oh, a lot of your labs look really archaic because they use archaic equipment. Well, that has to come from academics because I spent 23 years in industry and I know what you encounter in industry, and it was exactly what we had in that lab. And then, so we did make some improvements there, but the active learning was the thing that I mostly wanted to improve there. So let's just see if I can make this thing run. First of all, this probably goes on anywhere on campus where there are laboratories. We had to clean up that darn thing. People had used the dedicated classroom for this thermal fluids lab. They used it as a dumping ground for decades. Anything anybody couldn't keep in their laboratory space ended up in 3160. It was stacked to the ceilings. It violated fire code. It had a whole bunch of other violations of fire code, which I think now we've managed to clean up and so forth. But you can see that is really a nice, neat room now. And if you look in the cabinets, they are neatly organized. Students can look in a cabinet, and this is, I think, incredibly important for active learning. Don't want to waste students' time in looking for things or determining if we do or don't have something. So students can look in these cabinets and they can see what we have. Now, another solution to this problem probably should be putting together catalogs of what should be in each cabinet and getting them on the door and so forth. But that will be violated almost immediately, making all of that work completely moot. At any rate, that was quite a task in cleaning this up because, of course, it involved surplusing lots of equipment, involved the university's surplus properties. Well, I spent months rewriting laboratories. The laboratories, well, we know, engineers do not communicate well, and so the laboratories never were anything more than just a sketchy set of instructions, and they really needed background material. They needed a lot of material that would not only explain to students what they were doing, but would provide some enthusiasm for them doing it, some historical background and so forth. So I'm just going to run through some of the minor stuff. As part of ABET requires that we have a senior capstone design course that has many of the elements of real engineering work in it. And mechanical engineering has taken this almost to extreme. Our senior design process, usually students have industrial clients. They're trying to build real things. Many of the projects are so darn challenging that I think graduate engineers would have a lot of trouble with some of them. Anyway, in order to sort of make a linkage between 3160 and that senior design, I had used some of this engineering initiative money to have students build a real wind tunnel that could be taken apart and pushed out of the way, brought back together again, and they could run real research grade experiments on the wind tunnel. That wind tunnel is finished. I'll show you a picture of it here. This is just simply a drawing of what it looks like. By the way, just so that everybody can say, wow, I really know some engineering now. Here is the various pieces of the wind tunnel. This thing is kind of a bit out of focus, isn't it? Anybody tell me? Looks okay? Where's the focus on this darn thing here? No, oh yeah. Oh, it's astigmatism or something. Okay, looks like I'm giving an eye exam. This is the section that draws air in from the room. This thing is a wonder to operate in a small classroom. Draws the air in here, and there's a honeycomb structure in the front end that straightens out all the airflow. Flows into a settling chamber where we basically allow a lot of the turbulence to settle out in there, and then drawn into This just looks like it's sort of an air funnel, and it is, but it has a very carefully prescribed profile that will avoid putting turbulence back into the air as we draw it into a real restricted section in here. This is plexiglass. Students can look through the test section. They can mount models in the test section and make measurements of it. And this long extended section out here is known as a diffuser. We need to somehow take all the velocity back out of the air before we release it into the room. Otherwise, it just musses up everybody's hair. And the fan that runs the whole thing is clear at this end. So this was quite a project, and it involved 6 students in this project. I really liked the idea of linking senior design to instrumentation that could be used in student laboratories, because it seems like it gave everybody a stake in doing a good job. It would provide bragging points later on and so forth. I'm unsure how well it really worked. I've not really done a good assessment, but it didn't work out as well as I had thought. There's the finished product: the fan, the diffuser, the test section, the flow straighteners and settling chamber. It turned out to be a tad bigger than we had hoped. And what it is, it's an inducement to keep your laboratory clean and dust free, because the minute you turn on a wind tunnel, all the dust bunnies roll out of every place and start blowing around the room. All right, turns out, you'll find it kind of funny. In mechanical engineering, we have poor communication from one place to another. And as the students were presenting this project at undergrad research day a couple of years ago, George Twitchell, who's been retired from mechanical engineering for quite a while, said, "Doggone it, if I had $10 for every wind tunnel we've ever built." One of those sorts of conversations. And it turns out we had what's known as a mezzanine wind tunnel in the building that hadn't been used in 14 years. It is a great research facility, and now my students in senior design are putting it back into operation. We've got it running again. Anyway, we've got yet one more wind tunnel. Because ABET had complained about the technological level of some of our laboratories, I put together some heat transfer laboratories that have these units, which are automatic data acquisition units. In them, the students can pick up temperature data from an experiment that involves a cooling fin, and they can get transient data or steady state data, and they don't have to do things the old way, which involve plugging a thermocouple into measurement wells 300 some times to take measurements. It seemed like overkill. Once you've taken a couple of measurements with a thermometer, you know what you're doing. And so we did spend some there. Now, active learning. People think of laboratories as being active learning. They aren't. This is a canned lab, in case you've never seen any. People just sort of grin. Yeah, we can make labs as canned as you like them. We can can the whole darn thing, right? The procedures, the report, the analysis. You've seen canned reports. This is especially true in chemistry labs, where they have a workbook where you fill in line by line what you've read. That's about the worst canned lab you can imagine. I don't know how satisfying they are. I haven't seen them since I was a freshman in college 46 years ago or whatever it is now. And so we wanted to avoid this. Oh, and by the way, the whole course, yeah, we just continue canning stuff. The course is nice and neat. It's compact, but it's canned. What I was really looking for was a open-ended exercise of some kind. And so I started this experiment by just saying to my class, I want you in the next 3 weeks to go verify Torricelli's law. I didn't tell them what Torricelli's law was. I didn't tell them who Torricelli was. And I just told them, I said, there is one piece of apparatus in this room that if you looked at it, it would scream back at you, Torricelli! Well, not all of them could understand the Italian, I guess. And some of them got the wrong apparatus, but most got the right one. This is pretty dark. It's kind of hard to see, and we don't really have a whiteboard in here. So, well, I would draw on the wall with my markers, but I'd probably never be invited back again. But at any rate, here were my expectations for this open-ended experiment. I gave them next to nothing to go on. I wanted them to research the question. I wanted them to look for suitable equipment. Once they got those, I expected them to develop a method and run the experiment and perform a thorough analysis of expected precision and error. In mechanical engineering, we expect students to be able to put together a credible, what's known as propagation of uncertainty analysis, so that we have a very good feel for what our expected errors are in any method that we might employ to measure something, and then be able to compare that against customer expectations and say, yes, this method will do the job. No, this method is not capable of doing the job, and so forth. Anyway, this is what I was hoping for. By the way, the apparatus that screams Torricelli, it is a tall cylinder, about yay, on a stand that you can put it down in one of the laboratory sinks. And it has a drain on the underside of it. It has a scale of liquid height on the side. It's nothing technologically, but it's perfectly suited to Torricelli's law evaluation, which I'll show you right now. So there are two ways to view Torricelli's law, as it turns out, which I thought would really baffle students, but it didn't. Turns out they were amazingly inventive. The one way to view Torricelli's law is that the velocity of water leaving holes on the side of a vessel carrying water, that velocity is related to the square root of the depth of the water over the hole. And since this is coming out very fast down here, the depth is great, you have a very flat trajectory and the water will spray out quite a distance. And up here, it's kind of a wimpy flow and it just kind of dribbles down the side, so forth. We can express explicitly how this should occur. That would be one way to verify Torricelli's law. Poke holes in the side of a vessel and go see how far water issuing from it would land. The other way to look at Torricelli's law is that it defines the rate at which water will drain from a tank through a given hole that is some distance below a water level, and you get a time to drain that's a square root function of time, once again. And that is what I really expect them to do. They would see that apparatus, they'd see this definition of Torricelli's law, they'd see the apparatus, a light bulb would go off in their head. I didn't know that it was a compact fluorescent and so forth for some of them. So how did it go? Students loved the lab. First of all, that was a gratifying experience right there. Students had just gone through all of these other very somewhat more canned labs in the course of the class, and I think they were a little underwhelmed. This one they really liked. And the evidence, if beyond them just telling me that they loved the lab, the evidence was that they did enjoy it because they spent so much time on it. They did a great deal of research. Some of them went into great detail on the history of Torricelli and Torricelli's law and all of Torricelli's various problems with the church and other people in Italy. This now took them into a related issue known as discharge coefficients through weirs and things like this in civil engineering. And there's a long history in that discussion. And many of them learned a lot about discharge coefficients and so forth. And it turns out they used a variety of apparatus. I didn't recognize there was another piece of apparatus in the lab. It was a box-like thing that had a valve on the side at one height. And it was on a stand. And what the students did is they would fill it with water to various heights, and then they would let the water out of it and see how far across the room it would shoot and land on the floor. They were making quite a mess, but they were learning something. That's how I treat my children. They're making a hell of a mess. As long as they're learning something, it's not too bad. And so they were looking at the other version of Torricelli's law and making an examination of that. So that was really interesting. I never expected to see that. Now, the people who did find the correct apparatus, there were amazing things that went on. Oh, I wish I had a whiteboard or something here. On the underside of that vessel is the opening through which the water drains. That had an orifice on it that had a very sharp edge on it on one side, and if you turned it over the other side, it looks a little more like a funnel. Turns out I'd taken two of the apparatus and turned it upside down on two of them and had it right side up on the other. So we had a very sharp weir on one and a funnel-like weir on the other, which gave the two of them different discharge geometries. And so they had a completely different discharge coefficient. The students, comparing their data with other students, said, golly, we're using the same apparatus, but we're getting such different results. And they investigated and found the difference and then explained it on the basis of what they observed. So I thought that was incredible. Personal assessment, they were forced to perform at a much higher level than we generally expect them in here because they had an extremely open-ended lab and something fun and challenging to do. Okay, so, this is just here's an observation versus theoretical curve fit with that apparatus. Isn't that great? Very gratifying to have data that looks like this. You know what? I'm done, man, but thanks for bringing it up here. Maybe I'll use it for something else. All right. Next. What should I do next? Well, I think it's done so well, I'm going to have an open-ended exercise every semester. So I need a new one. What do engineering students, what do all students do? They try to take your open-ended lab and they try to turn it into a canned lab again by going back to their friends who took the class last semester, finding out what they did and getting their notes. It will now be canned if I repeat it. So we do a different lab. This time, what did I do? Well, I thought I'll have them investigate what are known as minor loss coefficients in valves and fittings, things like that. So I'm explaining the minor loss coefficient here. And by minor loss coefficient, what engineers mean is most of the loss in piping systems is caused by fluid friction with the pipe. Every once in a while, you run into a fitting or a valve, and it causes a little bit of additional loss on top of it. We say, you know, there are only a few of those in the system, so they're a minor item. We're going to see that minor is a relative term here in a second. So in this diagram, I've got fluid flowing into what's known as a ball valve here, and you know, if you measure the pressure along the line, you would notice that the pressure declines rather slowly along the line, and it's caused by fluid friction. Suddenly you get into this strange thing that changes the way the line looks. There's a little bit of turbulence, there might be some flow separation, there might be some recirculating flows in there, and you suddenly get a larger pressure drop, and then the slow pressure drop continues. That small pressure drop right there, we divide by the kinetic energy density in the fluid flow to make it non-dimensional, and that means that engineers can apply it to different fluids, they can apply it at different velocities and so forth, but that becomes our coefficient then. So here's the equipment we used. This is a piece of PVC pipe. We put a PVC ball valve in it. It's just an open piece of pipe. It's got a couple of measurement ports right there and there where we can measure pressure. So we measure pressure because the pressure drop is really small. We used a very sensitive pressure gauge. The units here, that's 1/10 of an inch of water column. In other words, it is the weight of a water column that's 1/10 of an inch high. That's a very, very tiny amount of pressure difference. These two hoses go out from the two measurement ports and go to the two ports on either side of the valve so that we can measure the pressure drop across the valve. And to figure out how much flow we've gotten so that we can get that V squared term, we've got a meter here. Now, there are all kinds of things that students have to do to get this done right. One is the meter is calibrated at sea level. Did they think to calibrate it at Laramie? Because it's got the less dense air running through it now. 3/4 of the students remembered to correct it for Laramie, and 1/3 of those students did it correctly. Okay, the unexpected occurs. Open-ended lab, didn't tell them what to do. During their research, there was one student, or maybe a number of students simultaneously found this. They went to a fluids textbook, one that we use in mechanical engineering. They found this table. Ball valve, fully open. It has a very tiny coefficient, 0.05. Ball valve, 1/3 closed, 5.5. Ball valve, 2/3 closed, 210. It's no longer a minor loss, right? What is the natural extension in here? Oh, ball valve completely closed, right? That's what they did. Very unhelpful. When you close the ball valve, it's no longer a valve. It is a part of your pressure system. So here's what happened. Valve open. We get a very modest pressure on both sides of that, and there's a very small drop, and we can put a very sensitive gauge in there that will read this very small pressure difference. Or in the case of the students who had the worst problem, they put in an oil-filled manometer, one of those things that has liquid that rises to different heights in two arms, and the height of the difference is related to the pressure. Okay, close the ball valve. There is now zero pressure on that side of our gauge. There's very high pressure on this side because nothing's moving. The air supply back here is 120 psi. The minute they closed the ball valve, they blew oil from the manometer all over the laboratory. I go, what were you guys doing? And they said, well, we were filling in this table, and I saw this ball valve closed entry, and I go, what in the hell were you thinking? Okay, here's an interesting one. Oh yeah, we destroyed one analog gauge too, so it turned out to be kind of an expensive learning. Anyway, question. How does this person supply critical warnings without alerting students to some sort of a canned procedure again? Because if you give them appropriate warnings about equipment, suddenly they have clues about what equipment they should go have a look at. And it just becomes easier and easier for them to fill in the details. Frankly, you cannot, in your wildest imaginings, figure out what students might do. So I don't think there's any way to give them critical warnings anyway. What's next? So I've done this for 2 semesters, and I've had really good results, and I had results that I thought were pretty good, but more mediocre. Obviously, we need new open-ended exercises. How many do I need? I figure if I have a half a dozen to maybe 8 that I cycle through, people will have graduated by the time they see the open-ended exercise again, and there won't be any recycling of that information. More careful attention to what they may do that's counterproductive. One of the other things that I've now seen, this morning, I was putting equipment away, and I noticed that the lab's becoming a junk pile again. And so it really requires some dedication to keeping the laboratory organized in order to make it a useful open-ended exercise. If I just turned students loose in there and said, have at that junk pile and see what you find, my guess is these exercises would never get done. I don't have to give them much organization, but I got to make things clear for them so they can at least see what's going on. So I don't have anything else to talk about. This is an ongoing experiment. We'll continue to see how it runs. But students really like being given their lead and just let them go and see what they will produce. And there are times I'm pretty disappointed in my mechanical engineering students, and something like this gives me hope for the future yet once again. So can I open it up to questions? Anyone have any questions? Yes, sir.
How does the timing of these labs compare with the canned labs?
Oh, this one? Oh, God. Oh, yeah. The canned labs, the schedule for this class is that I teach them an awful lot about data analysis for 2 weeks in the front end. Then we have a safety day. Everyone has to have a safety day, or they're not allowed to be turned loose in that lab. After that, they perform a laboratory. They write the report, turn it in, have another laboratory. So it's basically a week at a time, including the oral reports and so forth and so on. When I get here, I've got about 3 weeks left in the term, and I just give them all 3 weeks to handle it. But you know, I don't mind. I think they did so much learning in those 3 weeks. I think they did more learning in those 3 weeks than they did in the previous 6, for sure. So it takes, yeah, it'll look like you're not doing a lot. And if you have, well, sort of anal mechanical engineers in the department, they'll complain that you're not doing much, but I think you're doing quite a lot. Yes?
Do you find that, or what were some of the things that you found writing besides the really strange way to approach it? I mean, were there things that you were like, wow, I didn't expect them to learn that? Or were there some other things outside of doing the completely random straight thing and blowing stuff up? You know, like were there other things you were like, I didn't really expect them to go that far, or I didn't
Well, as I said, I never expected them to notice the difference in the two orifices, one turned upside down from the other. I never thought they'd see that. In fact, they did. And then they dug and investigated to figure out why that made a difference and so forth. I didn't fully expect that, but I was pretty impressed with them. Could they adapt to getting a piece of equipment that really wasn't very well suited to Torricelli's law? Doggone it, they did. They could adapt to it, and that was amazing. Another thing that I found that's interesting, we have about 4 dozen students in this class every term. You would think that in a random sampling of mechanical engineering students of size 48, you couldn't find a dime's worth of difference in the average performance of the class. I have found out that that is not so. There's a huge difference in one class to the next. The people who were doing the Torricelli's experiment are now my senior design students this year. The people who were doing the minor pressure laws are going to be senior design students next year, and I'm fearful. That's all I can tell you, because the classes are so different in capability. It's really, I think, fascinating. There, yes.
So I'm curious about how much perspective that is. Okay, there's this really ill-defined, open-ended question. How much do you get, sort of begging for more specific information, or your students are happy to just run with that complex, sloppy question?
You know, it's interesting because the students that you see in this class, you'll eventually see in senior design. In this class, there was no pushback at all. They were so anxious to try things on their own, and they didn't come and beg me for information. They would come and tell me what they had found. That's what they were excited about. Senior design becomes something different. I don't know why, but there's an awful lot of hand-holding that people want in senior design, or at least certain groups do. There are students who are really, they're just gung-ho on getting started on a senior design project. There are others that want a lot of hand-holding. Those same people came through the fluids lab too, but I didn't see it. I didn't see that behavior there. Don't know. But
if you institute this more throughout the whole program, like every single class at the lab that they did this, would change their perception of design, because they were used to it, right?
They would.
Be strange.
They would. And we have a problem in mechanical engineering in that the real professional faculty are trying to train engineers through their choice of courses in the curriculum. They're trying to train mechanical engineers for graduate school. We're actually trying to graduate most of our mechanical engineers into industry and the job market, right? And there's a terrible disconnect there. So what happens is, ABET has told us, you have to have a senior design project. What they do is they say, oh, that means we've got to give them some practical classes here and there. And the faculty deliver all of that with an eyedropper to make sure they don't do too much, right? Because they want to do more theoretical classes. Here's my general view of it. Theoretical engineering is for 5% of engineers. The 95% of engineers that we graduate get so little good out of it, they don't retain any of that real theoretical material. Anyway, they need more practical classes. And we probably there was a time when mechanical engineering was 144 hours to graduate. It was a 5-year program. We probably need to go back there. But no one has the gumption to make that case to the administration or to other people.
The 99%, or 1%.
Yes.
That may be going to graduate school still needs the practical foundation.
Yeah, because eventually they'll do people no good at all. Yeah. These are all really gnarly questions that probably all of you face everywhere. Yes. Where to strike that balance? And I don't think we do a very good job of it in mechanical. Now, Do we graduate pretty solid students in mechanical? We do, because we have a good reputation with people who hire our graduates. Our graduates are all over the place. Bremerton shipyards must employ 50 mechanical engineering graduates from the University of Wyoming over the past decade. They just come back. The nuclear shipyards up there, they just come back after our engineers constantly. So we do a pretty good job there, but we could do just a superb job. But as you know, that we've got this other issue. We're trying to become a tier 1 engineering school. We don't have the resources to do that. We don't have anywhere near the resources to do that. But being tier 1, I think, is an awfully heavy theoretical curriculum that just impresses people. I don't think it does that much good.
If you could, would you add another, would you have a couple of these labs in one semester, or is one thing?
We have the following laboratory classes. We have the thermal fluids lab. We have a mechatronics course, which is meant to combine mechanical engineering with electronics and microprocessor control. That one should have more practical experience in it too. We've got one that's called design of experiments, where they learn how to do, well, they should learn how to do factorial experiments, but they don't. Not really, but they learn a little bit about design of experiments. And we have a laboratory in what's known as system dynamics, and those laboratories tend to look like electronics laboratories. They should have a lot of other exercises in them. All of our labs could use improvement, and all of them need some open-ended experiences. That would help senior design a lot, because they would now have much more confidence going into senior design to say, by God, I need to go find this, and I need to do these tests, and I need to design a method here, and I got to make a case for buying this, and on, which are all engineering skills that they need later in life. They could learn them really well through a sequence of 4 labs and a senior design, whereas right now we're really hoping they just learn it in senior design. That's pretty tough to do in one class. Our senior design is a year, by the way. It's 2 course sequence.
Do you think you could, or would ever want to, design an entire lab class that is all?
Yes, I would. There would have to be some front end to it that brought everybody to a certain baseline. But yes, something like this. And as you know, they do this at MIT, right? There's a huge amount of just open-ended classwork at the really top-notch engineering schools, the ones that refuse to put up with ABET. MIT and Caltech will not put up with the Accreditation Board for Engineering and Technology. They said, basically, go to hell. We've got good enough reputation. We don't care about you. So we can't get away with that here, but we could design a lot of open-ended stuff, and you know, there are ideas galore. Budget's a problem now, right? We're doing a really interesting project for NASA at the present time in senior design, and all we needed this morning was a postal scale so that we could mass a bunch of the components and provide NASA with a mass balance for this project, this package we're going to send up and drop from 100,000 feet. And do you think we could find one anywhere in the College of Engineering? Turns out there's a Mettler analytical balance down in one of the chemical engineering's labs, but I had to now ask for permission for my students to go down and weigh batteries and stuff like that. Oh yeah.
You know, that's where you
No, I tried there. Nope, there's no postal scale there. They're depending on some other postal scale elsewhere on the campus. We're getting down to the point where we're normalizing the campus too much, right? Any other questions? Well, thanks very much for listening. You know, I was scheduled for an hour and a half, but golly, we're just starting on this experiment. Yeah.
leave it just a lot of, you know, questions and stuff, and sometimes but it was really, really great. It's really fascinating. And I know that, I think, are you from physiology? Yeah. So what do you?
So we're teaching other classes. Wow. They do a lot of it. Biology, but I've noticed through teaching, I'm only a second graduate student,
second semester. The first semester, there's a huge pushback from students that want to be at everything, obviously just because they came out of high school. To it.
Oh, so these are freshmen that you're dealing with.
Sometimes it's kind of difficult to get them to think out.
Yeah.
So it's a little bit of a challenge. I think it's better overall.
Sure.
If they're going to go on in science.
You know, you've brought up something kind of interesting here too. You were talking about the amount of pushback. A long time ago, in the mid 1970s, I taught chemistry labs. And there were a lot of medical students in those chemistry labs, and the medical students seemed to need more hand-holding than anybody else because, well, number one, they were freaked out about their grades, about getting into medical school, but they wanted a lot of hand-holding. And so when you brought up biology, I thought, you have an awful lot of medical students. And of course, if you're from kinesiology, it's sort of medical, basically, right? It's,
So anatomy, there's no experience. And that's actually so then there's TA for undergrad that help me. And we split up what they're supposed to learn that day. So like we just learned the cranial bone class. So there's different sections in the lab manual. We have four home groups, one with each of us, and then we send them out to expert groups, and they learn it, and then bring it back to their home group, their home group, and we just sit there and answer questions, essentially. So really, that lab is meant for them to teach each other.
sure.
Versus us pointing and doing everything for them. And then exercise physiology is more about like energy systems. So
Do you have any laboratory component in there?
the XFIS?
Mhm.
Yeah. So the XFIS lab, like this week, is energy systems. So
Okay.
they do start to jump vertical tests and queen step tests, and they compare their energy output, their power output, and then we have a gate cycle test. There's no open, yeah, there's no.
No, but the anatomy sounds exactly like open-ended over here because those are students teaching one another. Same thing. Yes? Right.
That's what we try. Sometimes it's a little bit more difficult depending. Like I teach 5 to 7, and then I also teach 7 to 9 on Thursdays. So sometimes my 7 to 9, I have to push a little more participate because by 7 o'clock on a Thursday, they're just gone. They're glazed eyes, trying to engage them possible.
Yeah.
Do you think that there's ways to do that exercise with that lab, which is, really quite, like no creativity. I mean, is there a way of allowing for some of that stuff? I mean, is there a way to figure out, ask them questions that might be really great, like, because they're all interested in the sports and stuff, so
It's a lot more difficult to get those open-ended questions than undergrad level labs. In my undergrad, my XFIS lab was awesome, but wasn't open-ended questions very much. But then the lab that had after that, we actually were working with clients. So like my clinical physiology lab, they had basically exercise on campus. So we had probably 40 to 50 faculty members from across the campus who would come in either at 11 or at noon every Tuesday and Thursday and work with undergrad students, and we would work out with them. We had to think about, oh, they had knee surgery, oh, they've had hip surgery, oh, they have a prime pupil. What can we do so they can?
Is our faculty in that bad a shape?
When you're on a campus that's about the same size as this, undergrad is the first semester.
Yeah.
And so if you take 50 people who want to work out and whatnot, usually the reason they're there is because they don't know it's because of the previous
Yeah.
because of the surgery. So
That
as opposed to a football player. And could you build on that, you know, to draw on their own experiences and their own interests to accomplish essentially the same thing, but just nuance it enough so that they could think, what does this look like when I'm a dancer? As opposed to what does it look like when I'm running football?
Well, so for example, you know, the Olympic test is it's a 30-second sprint on a bicycle, essentially, where in 30 seconds it drops 7.5% of your body weight in resistance onto the bicycle wheel, and so it's seeing what your power outputs are, your peak power output, and everything. And so yesterday we had 3 students of the lab of 16 do it, and we had one kid who was all endurance, that's all she does, endurance. And then we have one kid who only lifts weights. And you could see, I mean, you can see that difference. You can point out that difference and get them to engage in that way, but that's when you're trying to just get an overall like undergrad picture of exercise physiology. It's really hard to be that precise with, you know,
You know, you mentioned that this course is energy conversion, and the definition of mechanical engineer is energy conversion. They're basically one and the same thing, looking at it from different ways. And we have to sometimes figure out if there are ways that we can kind of combine mechanical engineering with some of these other disciplines. A number of you know Chase Roulier, the center for the University of Wyoming. He graduated this year. He's a huge guy. Chase is, my guess is he will probably be picked up by a team in the NFL. He's a really good center. I think he was all conference. He's a mechanical engineer. And I was just mentioning to him about his upcoming career here. Sports injuries, football particularly, are all dynamics and strength of materials related. And that's what mechanical engineers know a lot about. Chase performs at a really high level, and he's got this other store of information about strength of materials and dynamics. He might make some really great contributions to sports injury reduction, maybe a whole bunch of other things, better equipment in the NFL. I'm pretty excited to see what he might be able to do eventually. But that's an unusual combination. Well, there's no reason why it really should be. Oh well. Any other comments? Questions? Well, thanks a lot for coming.